I'm Ed China and I love technology. Now you may have seen me messing around with old cars or strange vehicles, but today I'm in beautiful Trondheim in Norway to find out what this clever machining tool has in common with this huge building in Taipei. Well, to find out we need to learn a bit more about vibration, so check this out. Vibration is an oscillation around an equilibrium point in a mechanical system. That might sound complicated, but a stringed instrument can demonstrate what that's all about. Energy is built up by stretching the string, and when we release it, what we get is an oscillation, a vibration that decreases if no more energy is added. And we measure the frequency in the unit of hertz. 1 hertz is 1 event or wave per second. There are good vibrations and bad ones. A speaker, for example, would work really badly without vibration. The same is true of an opera singer or an echo sounder. But usually, vibrations are undesirable. They consume energy, generate noise and damage both equipment and people, which is why we use a variety of methods in an attempt to dampen them. Everything from sound dampening all the way up to seismic base isolation systems in large buildings. All objects have what's known as natural frequency, which is the frequency at which the object tends to oscillate when affected by forces like impacts, winds, tremors, or imbalance, for example. If the frequency is strong enough and within our hearing range, we'll hear a sound or a noise. In cars, which of course is my specialist field, there are hundreds of different solutions designed to dampen every possible kind of unwanted vibration. When it comes to machining, it's particularly important that vibrations are kept under control. So I've come here to Sandvik Coromant, the leading company in vibration-reducing technology for machining, to see how they do it. And for an engineer and tech nerd like myself, this is nothing less than Shangri-La. So Tormod, can you tell me, what are the challenges with vibration when it comes to machining?
If you have a cylindrical tool, approximately 3 times the diameter, that's the maximum length you can go with a solid tool.
Okay.
And if you have a damp tool,
then you can go
much further. The steel has a certain stiffness. Approximately 10 times the diameter, steel has the end. So you cannot go especially further with steel.
So even with a damp tool,
even with a damper, because the
okay.
stiffness of steel isn't high enough.
Yes.
And then you have to go with carbides, or you have to reinforce it to get it stiff.
Wow, so the carboid is actually the same material that you'd be making the cutting tip out of?
Cutting tip, yes.
So how on earth do you machine that?
That is a big challenge, because it's a really hard material and can only be grinded with something harder.
Yeah.
And that is diamond. Yeah.
Where is the damping bit? Is it sort of all the way through, or is it just at one end? Or?
Of course, the vibration is in the front, so you would like to put the damper at the insert.
Right.
That would be more efficient.
Yeah.
So it's placed as far to the front as possible.
Okay. So then the damping magic, if you like, is inside here. So you've got, I can see some O-rings.
Yeah, you have to work with 3 things. That is the mass, which is a damping mass, because it's a tuned mass damper, and then you have some springs.
Yep.
Because you need to tune to the right frequency.
Okay.
And then you have something to add damping, which is oil.
An oil, actually, so it's very much like a car suspension, where you would have your spring, obviously, to keep your wheel going up and down, or whatever, but then also you'd have the oil in the damper itself to absorb that vibration. Silent Tools uses a damping technique known as tuned mass damping, where a relatively light counterweight inside the tool absorbs kinetic energy of vibrations and uses a compensating frequency to eliminate them mechanically, rather than converting them into noise and heat. Hence the name Silent Tools. Now Dan, these tools come in all shapes and sizes, I guess, so is this the smallest that you manufacture?
Yeah, this one is the smallest. It's 10 millimeters in diameter and 10 times T in length.
Wow, okay, so that is actually going quite long.
Yeah.
And you've got all the damping technology in the tip of this, as before.
Yeah.
That's amazing. That is really crazy. So that is quite one extreme. So what would be the longest tool that you could do?
Yeah, measured in times D.
Yep.
That's the longest tool we make.
Right, and what is
That's
that?
18 times the
18
diameter
times
and 100 millimeters in diameter.
Wow, that is amazing. So, I mean, that really is pretty extreme. I mean, would you say that was the most extreme tool that you do?
Not really, because it's still quite stiff because
Because it's 100 mil diameter.
Exactly. Well, this one is more extreme and harder to make to work.
Oh, I see.
Because it's less diameter and 14 times D.
I mean, obviously in this world of computers and stuff, is an active tool sort of where you're headed, so you know exactly what's going on all the time?
Yeah. The tool over there that we looked at before.
Oh, well, that's it?
That's it.
Wow. Okay, so that's obviously connected up to this machine. So, and that's what the screen is then. So can I try and deflect it? See what happens?
Yeah, you
Okay.
can try and push it.
That sounds like a challenge, but...
Yeah.
Oh, wow, look at that. So what am I managing?
So that's 0.4 millimeters.
0.4 millimeters. That sounds... I mean, you know, I'm giving it some. Can we see it actually operate?
Yeah, sure.
I mean, is it like a normal, like a lathe? You'd actually have to set the tool up to make sure it's the right height and the right orientation?
Yeah, that is what the operator will start with, is to look at the tool setup. That's a level, a digital
So
level.
it knows where it is in
Yeah.
space as well?
And we have the live view screen here, which
Oh, so you've
shows
got
us,
temperature as well?
yeah.
Yeah.
So it shows us the deflection and the load of the bar.
Yeah.
Total load is very important to know.
Of course.
And
Yeah,
then
yeah.
we also measure the vibration level of the tool, which is very related to the surface you actually get in the end.
Of course.
So these are also two very important
Yeah.
features that we measure.
Fire her up, please. Remember the skyscraper at the beginning? Well, it's called Taipei 101 and it's located in Taiwan. And what's interesting is despite its enormous size difference, it actually uses the same system as Silent Tools, tuned mass damping, to counteract vibrations and oscillations brought on by hurricanes and earthquakes. Their counterbalance, however, is slightly bigger, measuring 5.5 meters in diameter and weighing in at 660 tons. It even comes with its own mascot, the Damper Baby. Wouldn't it be cool to make a model to see exactly how tuned mass damping works? Well, I thought so, so I got my friends here at Sandvik Coromant to build one. Hi Greta, how's the
Hello,
machining
Ed.
going?
It's going very well. You want to see?
Yes, please, yeah.
Put your glasses on.
Absolutely. Look at that, that's fantastic.
Yeah, gorgeous, right?
Well, thank you, Greta. That is wonderful.
go.
Thank you. Look at that. I have Greta's part, which is great. So just maybe sand off the edge here.
Yep.
So Karen, should we start attaching this? There we go. I think we're good.
Yeah.
Yeah. One more to go.
Nice.
So that's pretty good, pretty good. Right, so now, obviously we have our tower, so there's a small hurricane,
Yep.
or maybe an earthquake. So what would be really good is to actually maybe measure the frequency to see what it is at
Yeah.
the moment, because it's obviously going to take a long time to just
Yeah.
die down on its own, isn't
It's
it?
a good idea. So now we have the laser spot here,
Oh yeah, okay,
Yeah.
fantastic.
and this is a Doppler laser. So this
Okay.
one measures the velocity
Oh, that's clever.
of
Okay.
this one. So now we can give it a small push.
Okay.
Yeah, and then we just wait. Let's-
Yeah, so obviously that's where Karen caused an earthquake or a little hurricane.
Yep.
And it's coming all the way down and down and down and down and down. It's basically it's taken so long the machine has got bored and just stopped measuring it. So in the same way with the silent tool, obviously we now need to have a tuned mass and then we need to damp it. So what we need now is our little ball, as you say, so our 660,000 kilogram ball down into a little tiny thing, and then we can put that
Yeah.
into position.
Yes.
And then once it's in position, we need to tune it, presumably, just to get it
Exactly.
so it vibrates in
Yes,
relation to the tower.
because we want the frequency of this one and the frequency of the pendulum
Yes.
to
Okay.
be quite similar.
Okay, so let's have a look at our pendulum. Now, what is this weight made of?
This is wolfram or tungsten.
Tungsten, so it actually is very heavy for its size.
Yeah, very high density.
Yeah. Okay, thread it through here.
Yeah.
Really. Just pop that down there for a start. So let's just get it so that it rocks the right way.
Yeah.
About there, do you think?
Yeah. Now we can see.
Okay, so it's got quite a fast sort of return.
Yeah.
So now if we lower that down,
I can change the frequency of the ball.
so now if we rock it again, so that's a much more kind of relaxed frequency.
Pendulum.
So that's more in tune with the wing. So this is exactly effectively what you're doing inside the tools, is you're having to change that down, or tune that mass so that it actually does this transfer.
Like that.
I think that's quite okay.
Yeah. Oh, that's really interesting. So you can see the energy from the tower being transferred into the pendulum, but then actually transferred back out again.
Yeah.
Excellent. So now the next thing is we need to damp this somehow. So obviously in the silent tools, we use a special liquid, like a viscous liquid, to do that.
Yes.
So presumably we can do this the same sort of way.
So here's
Our magic fluid,
some oil we can use to get some damping into the system.
probably completely top secret. Excellent.
Basically.
The magic ingredient.
And it will be really interesting to see how this will work. And give it another earthquake, maybe?
Oh, please, yes. One of your finest earthquakes. Oh,
Look
wow.
at that.
Do that again. So now in a car, obviously the trick with the suspension is basically kind of 1.5 bounces. And just to do that again, you've got kind of 1.5 bounces.
Yeah.
Look at that. That's amazing. Well, that is incredible. So our model tower is now completely resistant to hurricanes and earthquakes thanks to tuned mass damping. And so clearly the physics works whether your tower is nearly 500 metres tall, whether it's a metre tall, or whether it's in a tiny tool. Yeah. I think we deserve a little round of applause. So now you know the similarities between this silent tool and Taipei 101. They're both subject to the same laws of physics and both damp vibrations with the same method, tuned mass damping. Until next time.